Okay, any question about the previous system? We want to talk about noise conditional score networks, and we will see that how the problems with both spliced score matching and denoising score matching can be solved using noise conditional score networks. We have previously seen 4 different losses. I do not want to repeat them completely, but we have the loss of explicit score matching. This loss has the problem of S data of X, which is intractable to calculate. Then we introduce the loss of implicit score matching of theta. The challenge was that, what was the challenge here? The trace, yeah. I just write the trace. Then we introduce the explicit score matching for the noisy data. What was the problem here? The problem was a score function for the noisy version of the dataset. It is still intractable. There was an alternative, denoising score matching with parameter sigma. What is the problem with this one? It can be calculated easily, but there are 3 problems that we talk about them here. Manifold hypothesis, manifold. The second one is, I call it low density region. This is coming from the Song paper, the topic of this challenge, and also the slow mixing. It means that even the denoising score matching, where we can easily calculate the loss, we can backpropagate it and update our model, has these 3 challenges. And now we want to talk about each of them and then talk about noise condition score matching, which is the solution to these challenges. And that's the final the model. Then we will transfer to the diffusion model using noise condition networks. So what was the manifold? We talked about the manifold hypothesis. The manifold hypothesis is that if you have 2-dimensional data, in general, if you have high-dimensional data, for example, MNIST images, they are not really lie in this dimension. Their true dimension is much lower than this number. And you can find, for example, an upper bound to that number using PCA. For example, you reduce the dimension using PCA to 600, and then you observe that nothing is lost. So you understand that the dimension, the true dimension, is even less than 600. Visualization in 2-dimensional is that the true data is usually in 1-dimensional space, while and this is not what what you have in reality. Scale it to the MNIST. This is MNIST. This is what we have really in MNIST. This is what we think we have in MNIST. It means that we think MNIST is of the dimension 784, but in practice MNIST is of dimension 300, for example. Here we think data is 2-dimensional, but in practice it is 1-dimensional. And what is the problem with this change in the true dimension is that there are some regions in the space that that is not the support of the distribution, and the problem is that we have write it. Here. The score matching objective is consistent only when the support is the complete space, is the whole space, and this is the problem. So this is the first challenge. we see that if you add a noise, you would, then the support will become larger and larger, and for enough noise added to your data, then the support will be the whole space, and the problem of manifold hypothesis is solved. So adding noise can solve manifold hypothesis, but we know that that's the noisy data. It is not the original data anymore. So this is the first problem. And this is the training, how adding noise affects the training of the data set. This is for slice score matching, and we see that when adding the noise, the curve of the learning curve is much more aligned with our expectation. The second problem is that if you have low density region inside your space, then the estimation of the score matching, the noise and score matching, or slice score matching in those spaces is not accurate. You can observe these 2 points. And this. Although for the high density regions, everything is ideal. It means that both the direction and the amplitude of the vectors is very great with respect to the reference, which is this one. This is a problem. S data of X, not theta. So this is the second challenge here, low density regions. We have problems. And the last one is to some extent intuitive. Assume that what I want to estimate is this mixture of two Gaussians. As you can see in this, pay attention to these two regions separate. If I am focused on this region, then the score function, this is the true data score function. We can change it to data because I know the formulation of the data. The true data score function is the logarithm of these two components, the gradient of the logarithm of these two components. And I know that the second component here is almost 0, so I can omit it. And then, if I take the gradient of the log of the P1 of X, then the effect of this P1 will be neglected. As you can see, you do not have any effect from P1. Everything is coming from the approximation. It means that if you are working with infinite precision, then these approximations are not valid. In that case, you also have the effect of the second component, and also you then as a result you will see the effect of the P1. Because when you cannot assume this part to be 0, then you can you have the access to the effect of this P1. So, but in the limited precision, which is in practice what we use, you cannot see the effect of the mixing ratio. This P1 and P2 is the mixing ratio of the components, okay? You cannot see the mixing ratio here in your score function. And you cannot see the mixing ratio of the second one here. It means that your score function there is no difference between these two regions for your score function. If you input several data points into this score function, then probably equal number of points will be here and equal number of points will be here at the end. This is the problem because you forget the mixing ratio. Assume that I take, this is IID samples from the true data distributions, because we got sampling from the true data distribution, we have lower number of data samples here and higher number of data samples there. But when you sample using LMC, then you will observe almost equal number of samples in these two regions. What happened here? I start from, for example, Gaussian noise, two-dimensional Gaussian noise, for example, with mean here and a covariance matrix, and then I run LMC for all of the data samples. And at the end, I observe that equal number of samples is here and equal number of samples is here. The reason is that your score function cannot understand what is the mixing factor of these two Gaussians. Because you have limited precision, in each of these regions, it forgets the mixing ratio. So as a result, equal number of data points will be here and here. This is the second problem. There is a very great visualization of this problem designed by Song. You can download it and watch it in his own website. It is a very great demonstration how this problem is happening. So this is the second problem. It means that if you use the naive loss of denoising score matching, then you have a slow mixing. This slow mixing means that your component, the mixing component is lost. What is the problem here? I start with several samples of Gaussian distribution. These are initial samples, okay? Then I have a trained model, okay? That trained model knows the score function of the approximation of this score, the score function of this true data distribution. So if you start with these points and using LMC, then LMC tries to approach each point to higher probability regions through the iterations, okay? Then what happened at the end? Equal number of samples will be at this point and this point. But in the true data, the mixing ratio of this region is much lower than the above region. And we expect the resulting distribution to be much lower number of data point here and much higher data point here. This is what we need and what we want to observe in practice. But what happened is this one. You have almost equal number of samples in both regions. Does it make sense why we have this problem? Yes.
Please go back to the previous slide. Yeah, I didn't understand how it ends up ignoring P1 and P2.
Yeah, if I can assume this part is 0 in this region, which is logical here, because this component is almost 0 in this region, then I have the gradient of the logarithm of this multiplication. It is the gradient of the logarithm of first plus second. The gradient of the logarithm of P1 is equal to 0. So I missed P1. Okay, but if I have infinite precision, then I cannot assume this part to be 0. It has its own effect, though, so you can observe P1. But in practice and in our models, because we have limited precision, you can. What happened is this one. The second component will become 0 in this region. Then you lost the mixing ratio, P1 and P2. These two values. Does it make sense what happened here? Yes.
So the gradient of log P1 and log P2 are still different numbers.
Yes. The gradient with respect to x, it's 0, both of them. I mean, this P1, we have two P1. This the Greek P. Okay. The gradient with respect to x of a constant number is 0.
Yeah, I know. But the gradient of S theta is the gradient of log P1 with respect to x. P1 of x, actually.
Yes. Yes. This is what we have written at the end.
Yes. So log P1 of x and log P2 of x, the gradient is different.
Yes, but you know, the mixing is the result of how the data is spread between these two components is the result of these two P1 and P2. If you start with uniform, with a Gaussian, for example, like this, then because the mixing is assumed that the center is these points, okay? then intuitively, these points will be go to this side, and this point will be go to this side. But why? Because the algorithm lost the mixing ratio. Which component is more powerful than the other one?
So P1 and P2 demonstrates how strong each mode is.
Yeah. It means that what is the effect of this ratio, this component in the complete distribution?
So
Assume that these two P2 and P1 are exactly the same variance. Then what you think is solved? Okay. Assume that they are of the same variance, okay, but different mixing values. As a result, again, you expect more points to be here, although they have
the same.
because it has a larger mixing value. You expect more to be here, but as a result of score matching, equal points will be dedicated to each of them.
Phi1 and Phi2 are distinct.
Yeah, they are ignored. Yeah. Yes. Do you have a question?
Could you go back to the slide where you're showing LCM and then explain why
LMC algorithm.
And explain why the LMC algorithm are both equally distributed points on both teams.
Pay attention to here. The LMC, as a result, LMC accepts the S theta of X as the input and then work on that to change the position of the data point, okay? What happens is that because your S theta of X does not pay attention to the mixing values, as a result, we expect more point to approach this region, but in reality, this model score function is not aware of those components. Okay? As a result, equal number of data samples will if you start, for example, with some with a distribution like this, assume that I start with a distribution like this. This is my initial data samples, okay? Then I will see much of them will be here, but we start generally with a uniform or center Gaussian distribution. And as a result, because the score function is not aware of the mixing component, then it takes equal number of samples to this region and equal number of samples to this region. LMC uses S theta to generate new update of the data point. LMC uses this S theta and that D vector to change this vector. So you update it to a new vector, and this new vector is whether accepted or rejected, not important. But after enough number of iterations, some of the points will be accumulated here, some of them will be accumulated here, and the problem is that the number of points accumulated in each of these regions is equal, and that's the problem coming from this idea. This idea. Yes.
I think for the video, when you're talking about the Greek letter pi.
Yeah.
Yeah, because.
We can call it pi.
Yeah, if you say it's a bit.
Sorry, yeah.
Confusing.
Because your algorithm lost the pi value, as a result, you cannot understand how many samples should be dedicated to this region and how many samples should be dedicated to this region, and as a result, you have something like this after generation using LMC. It means that the number of points in each of the components will be almost equal, while we expect the number of points at the top one to be much larger than the lower one. Any questions? Sorry for the misunderstanding of P. I will change it to alpha or something like that. Okay? So we have 3 problems, and we now understand all of them. The first one was the manifold hypothesis. The second one was the problem with low density region, and the last one was the slow mix. And we know that these 3 problems will remain in both slice score matching and denoising score matching, and we need something new. That new idea is noise conditional score networks. Sang and Ehrman observed that perturbing data with random Gaussian noise removes these three obstacles. Perturbed data will not be confined to low-dimensional manifold. We see that how it can solve the problem. Gaussian noise can fill the low-density regions and can provide more training signals for training. It means that the low regions will be higher density regions after you add the noise. And sampling from a score-based generative model can overcome the slow mixing of Langevin dynamics by sampling from a set of models with decreasing noise perturbation level. This third part is not clear now, but we will make it more clear at the end of this presentation. So what happened in noise conditional score networks? We start with a family of variance values. This is a positive geometric sequence such that sigma 1 over sigma 2 equals sigma 2 over sigma 3 until sigma L minus 1 over sigma L, and all of them is greater than 1. It means that the smallest one is this sigma L and the largest one is this sigma 1. So instead of one noise variance, you have a sequence of noise values. This is noise variance. Again, sigma 1 is the largest, the most noisy version as a result of perturbing with sigma 1, and sigma L is the smallest one. So what happened next? You start to generate the noisy version of the dataset. We know that using each of these sigma values, I can generate a new dataset, which is a noisy version of that true dataset, and the new distribution for that dataset is something like this. I know that with using sigma 1, I have the most noisy version, and with using sigma L, I have the nearest distributions to my original data distribution. What happened to train a conditional score networks? We train a function s theta of x and sigma, which is known as noise conditional score networks, which is the name of this method. And this function can estimate the score function of the noisy data at each level of sigma. This is the new version. Yes.
It says the obstacle. Is it talking about all three obstacles mentioned on the previous slide, or just one of the three?
Where is the obstacle?
Large enough to remove the obstacle.
We know that if you add more and more noise to your data, the problem will be more easily solved. Both three problems. But if the noise is large and large, then you miss your data. There is a trade-off here. Okay? Yes?
How come adding noise solve the second problem, the low density?
Because the data points are flexible data points, and they can move around their points. Previously, they were fixed points in your data. Now they are flexible points. So the support of the distribution is larger than the support of the original data set.
What do you mean by support?
Support means that the points that the probability is non-zero. The point that the probability is non-zero. Okay? So, we want to design a model that can estimate the score function of your noisy data set at a given noise level. Assume that we know that, what was the score function of, what was the optimal score function? Remember the denoising score matching, and we see there that the optimal score function for the noisy data set is equal to 1 over sigma 2 of x tilde minus x. This was the optimal, and we know that we cannot achieve this score function. Here, you have something like a radio that has a tuner. That tuner defines how noisy is the input, and then the score function can denoise given the value of the noise added to the data. It means that you should give this system how much noise do you add to your data set, then it can denoise it. It means that it is a tunable denoiser. Does it make sense how it works? What we have previously is that in the denoising score matching, you estimate the S theta of x tilde, means you estimate the score function of the noisy data. If you give this function, for example, noisy version of the ImageNet, then what output using this network, what was the output? The output is the difference of this value, and then inside this function, the function estimate x, which is a hard task, estimating the denoise. It means that inside this function we have a denoiser. Internally, it estimates this 1, and then the difference of these two divided by this noise value is output. Something like this. Just the noise is added, output, because the difference is output. Now you have a much more powerful denoiser. This denoiser both understands the noisy input and also accepts a value of noise added to this data. This is the actual value of the noise. This is not an estimation. You give the model both the noisy data, you know how many noise you added to this data. Then you input the value of the noise variance to the model. Noise variance means the noise energy, how noisy you make, how much noise you add to your data. Then the model, based on these two information, can output this value for you. Okay? So, in the noise condition score network, we have still a score function estimator, but this score function estimator is a tunable score function estimator. It means that it can understand what is the input, how noisy is the input, and then denoise it at the output. Yes?
How is this different than like not denoising autoencoders?
Denoising autoencoders are also generative models, can be considered as generative models, but because their middle layer is not, let's say, has not a predefined distribution, then you can't use them for generation. We know that variational autoencoders are generative models because the middle layer, the code, has a predefined distribution and which is near to the prior. But the denoising autoencoder cannot be used as a generative model. Here, the output is the direction. What is this direction? This direction shows if you add this value, this output to your input with a step size, then you increase the probability of your distribution. Which distribution? The noisy data distribution. We know that this score function is the score function for the noisy data. Pay attention to this point. We replace L of denoising score matching instead of they are equivalent objective optimization. Objective with what? With loss of explicit score matching with parameter sigma. It means that the loss of explicit score matching for the noisy data. So this output shows you how you can increase your probability in this distribution for your input. We know that we just have access to the score function of noisy data in this approach. Okay? Everything is clear? Yes.
So in the figure that you plotted, I didn't get the role of that sigma, the tuner mode.
This one?
The noise vector.
Typically, this model is of type of, I don't remember, is of type of unit models with time parameters, okay? they accept something like this sigma, and this sigma is not behave. They do not behave this sigma as an input similar to x. They use it to modulate their architecture. The architecture is to some extent complex, but you can assume that it is another input. It means that the input to this is of dimension d plus 1, and the output is of dimension d. And then you generate this sample. You generate the noisy sample, because this is during the training we will see that how you generate the sample. You generate this sample, you know that how noisy is this sample, then input that noise to the model too.
So you input the same noise?
Yes. This is the noise corresponding to the what you add here. Yeah.
So in this case, what's the difference between like the previous model that doesn't have that input as a noise?
Yeah, the previous one was designed for just one value of sigma. But here it is a tuning, because sigma can be these values. Sigma 1, 2, till n. Yeah. Any question? Yes.
Well, why is it important to have the HU metrics? It's not just...
Yeah, the most important point is that we know that if we add more and more noise to our data, then the challenges will be more easily solved. Another point is that if you add more and more noise to data, you are escaping from the true data distribution. So what should we do? We start our approach by using a large value of noise, and then during the training decrease the value of sigma so that we approach the true data score function. This is much more, this gives you much more better performance than using just one value of sigma. Because if you use just one value of sigma, then you should stay at the point of this trade-off. Even you are not approaching your true data distribution, or you have those three challenges. But using a sequence of sigma, you simultaneously solve the problem of those challenges by starting from large value of sigma, and then approach your true data set by decreasing the sigma value during the generation process. You will see that how you can generate using this sample. The generation is completely different here, because you do not have how to generate samples using LMC, Langevin Monte Carlo, with something like this function, because this function accepts another input. How can I provide that value for the Langevin Monte Carlo? We will see that how we can solve the sampling. So just pay attention to the fact that this model can estimate the score function of the noisy data set at several levels of noise. Okay? This is the model. The model is anything again, CNN, fully connected RNN transformer. The input is of dimension d plus 1, but we know that they are behaved completely differently, because there is much more abstract information here than these points. It is the information of the noise in your data set. So it is a much high-level information here. So you cannot process them for example, in a mixed way. You cannot append this data to your data and use, for example, a full connector to transfer. You should behave it differently. You can look at the architectures. They are not very hard to understand. And at the output, you have the score function at that level. It means that you have the score function of the noisy data with the input sigma value. Okay, now we have the model, and we should train this model. Okay. So for the simplicity, assume that I have just one value of sigma. I do not have the I do not have the sequence. As a result, I can easily train the model using the denoising score match. Then I have one value of sigma. We know what is the learning process. I can solve this problem. I start by sampling from the data set, then add noise to it, and then calculate this value, backpropagate it, update parameters. So nothing's changed in comparison to denoising score matching because you have just one value of sigma now. And we know that when I solve this problem, I have the score function for this noisy dataset. In general, how you train the complete score, conditional score network objective using this function. What is this? This is just an extension of the above. This is the LDSM sigma 1 here, and you just weight it using something like lambda of sigma I. This can be easily selected using this value. What happened? Instead of optimizing for one value of sigma, you are optimizing for several values of sigma. And during the training, you have several of these terms. It means that starting from one data sample, let me write it here for better understanding. I will add this to the presentation in the future, but I just want to write it for two values, okay? To understand what is happening. X of P data, exponent, I do not write the distribution. This is something here, plus, here for example, I use sigma 1 to the power of 2. Sorry. This is sigma 1 to the power of 2. This is sigma 2 to the power of 2. 1 over 2, exponent with respect to data, exponent with respect to noisy data, and this function. I want to optimize this objective. So I need to replace the expectation with Monte Carlo estimation. Again, just one sample. I sample from the data set here, then I add noise to it, and then I calculate the denoising score matching value, then backpropagate it. For the second term, again, I sample another data. You can use the previous one, but for the sake of diversity, you can sample another data sample, add another level of noise, and then update your model. Pay attention. The model is aware of the noise here. You know, it means that for the first and second one, not only you change X, input X tilde to your network, X tilde, you change this sigma. For the first term, the input is sigma 1. For the second term, the input is sigma 2. So it should be such that it can understand how much noise is added to your input, and then tune its parameters so that denoise that input. And this should be generalizable along different noise level. Very powerful model, a model that can understand what is the noise level, accept the noisy data, output a denoised version. It is a very powerful model. Generally, we have model trained for a level of, in the denoising, for example, literature, we have models that can work on just one level of noise. But here you have a powerful model that can work on different level of noise. Yes?
So is it that you do not do it, like you do it randomly, you choose L randomly?
L?
Okay.
No, L is predefined. The number of noise levels.
Let me rephrase my question.
The L is the number of noise levels.
Yeah, I think I meant I.
I.
Because you're going to pick all the different types of noise.
I understand. You know, this is the summation. You can consider, this is what happened in diffusion models, okay? In the next level, you see that we can interpret this summation as an expectation. This summation as an expectation over a uniform selection of this I. This is exactly the definition of summation, expectation, okay? But in noise condition score matching, how it can be generated, it can be assumed as a summation. We can assume that it is the expectation over random variable I coming from uniform between 1 and L of this function. lambda sigma I of L. This is when you replace this expectation with the definition of the expectation, you easily use the probability of each I, which is uniform 1 over L, and the value of the function you have. But in the noise condition score matching, they do not have this approach. In each iteration, they update all of the terms. It means that for each update, okay? For each update, first you sample L different training data, x1 till xl. These are sampled from the training sets. Then you add noise. X1 is for the noise level number 1. So you generate x1 till. And you know that this is the result of adding noise with this variance until the end. X tilde of L, and you know that this is a much lower noisy version. This is the highest level of noise, this is the lowest level of noise. Then you input this to your model, and the model, when accepting this one, should output what? What is the output of an ideal model for this input? 1 over sigma 1 to the power of 2 x1 tilde minus x1. You train this model. The input, the output. You can easily train it. And also at the end, for this input, you should output 1 over sigma L to the power of 2 xl tilde minus xl. Input, output, input. You can easily backpropagate it. Yes.
So this is like a joint optimization that considers all the noise levels and.
Yes.
And wouldn't we have a scaling problem
Scaling problem?
Yeah.
Why?
You have like different noises and different objectives too.
The scaling, you know, when you have a noisier version of your data, okay, we know that the training, this one is, let me check. Yeah. The noisier, the scale of each data, for example, this is the most noisy version, okay? At the same time, it has the highest scale. It means that you pay much attention to the noisier data, to the lower noise level, because the scale is this one. But it is something heuristic, this option. And then select this option and it works in practice, yes. Noisier version are given higher power in the optimization. Any question?
Yes.
Why?
Why give more power?
Because they are harder to denoise.
Okay.
Conceptually, if a model can denoise the very noisy data, it is capable of denoising simpler ones.
So intuitively speaking, should we start with like little noise and then keep
Training or sampling?
Which of?
Training.
Training?
Yeah, start with like small noise and then keep increasing it.
Maybe they have some consideration in that respect too, but I think generally in one step they apply the backpropagation of all of the terms. It means that all levels of noise collaborate to update the model. It is not started with higher level noise and then add the lower level. I think they are uniformly sampled and then shown to the model and then update the model. But you know that the basis change is different. The higher level noise are more effective, okay? Any question? So this is the training. At the end of this training, we have a model which accepts the noisy data, the noise level, and the noises. So what can we do with this function, with this function? How we can use it to sample? Because the objective is to sample from the generative model. How we can use this S theta of x tilde and sigma 1 to sample from that model? This is the most important question, because we do not know how to handle sigma value. If it was it was just X tilde. We know Langevin Monte Carlo can solve the problem. But with having some parameters like noise, how we can handle it. And the great idea is here, which is called the name is this one, Annealed Langevin dynamics algorithm, ALDO. We will use ALDO for this function. What happened here? After the training, we have something like S theta of x and sigma, and you know that this function is not capable to handle any sigma values. Pay attention. It just can handle the sequence you select in the training. You cannot use arbitrary value of sigma for this one and expect the model to output something meaningful. Okay? Because during the training, it just maybe it can generalize for the middle values, but you cannot. It is not guaranteed. Okay? We have a pool of L score functions. We have a pool of score functions. So what's your idea? Which of them we can use to sample? We can select one of those pool, one of the element of that pool and use it for LMC. This is an option, and it is an option because previously using denoising score matching, you do the same. Maybe using the information of the different noise level improve your estimation for one specific level of the noise. And then you have a better generative model. But there is better idea to use this pool to generate sample. And we will see that that's the annealing version. So S theta of x and sigma L is the score function correspond to the nearest random variable to x. We know that this is the let's say the denoise the least. Then the data set with least noise, okay? What happens if we use this one? Assume that I put aside all of them and just use this one. What happened? What's the challenge? I use the denoising score function of the least noisy version. What is the problem?
I think the three problems you face.
Exactly. The three challenges. The three challenges appear when you are using the data with the lowest level of noise. Because we know that in that case we have, let's say, manifold problem, low mixing, and also low density regions. Because the data set is the nearest one to the true data. And the true data have some problems. So I cannot use this alone. If you use S theta of x and sigma L, then you have a slow mixing of Langevin dynamic. Simon and Herman proposed annealed Langevin dynamics ALD or annealed Langevin dynamics algorithm to make the use of all value of sigma values to solve the slow mixing of Langevin dynamics. Why do we emphasis on the slow mixing? Because the other two challenges are generally related to the training. This one is related to the sampling. We see that when you have a slow mixing, then if you start with uniform data point, then equal data points will be assigned to each of the components, which is not aligned with the true data distribution. This is what happened in sampling. So we are focused on slow mixing of Langevin. And the general idea is as follows. You start sample x tilde from Q sigma 1 of x tilde using LMC. This is what we have previously. Using one level of noise, you can easily generate samples using LMC. Is it clear? For one level, we can easily, yes.
Just to clarify, I mean, this way of approach solving the previous problem because like each points now has like degree of freedom to move around the space, right? That's why it's able to like solve the three problems before.
Yeah. Yes, exactly. You know, but when they can move, they can explore the space. the space, some places in the space is unexplored in the true data distribution, and when your data can move, it can explore those space and put light in that space. That's the solution. Yeah. So what happened? We start with the highest level of noise, use the score function of that data to generate samples. What is the problem with the generated sample here? What is the problem with the generated sample at the end of the system? Is there any problem with that sample? What? Yeah, it's very noisy because it is data coming from the highest level of noisy version of your data set. It is not working. It is to some extent something like garbage. Because it is coming from the score function of the noisiest version of your data set. So we end at a point which is corresponding to the noisiest version of your data set. What do you think? What can I do? How can I use the other score functions to improve this point? I have score functions of better data set, nearer to my true data set, but I do not use them now for this sample. Okay?
So you have to sample using sigma 1 and use the sigma L to somehow find its value.
Yeah, that's an option. You start sample, you use S theta of x tilde and sigma 1 and generate something like, for example, this x tilde, let's say 1. We know that this is we do not have slow mixing here. Why? This is the noisiest version, but this is not a great option because the dataset is far away from our true dataset. One option, as you said, we can input this x tilde 1 into a LMC with S theta of x tilde and sigma L, and then output a great sample. Why? First, this point we do not have a slow mixing because we previously solved it to some extent. We are near to the true data. Why? Because you are using the score function of the best option. This is a great procedure. But why do not fill in between? You have a sequence of score functions. Each of them, one step you approach your true data distribution. So instead of having a discontinuity here, start with this approach. Input this one with LMC using S theta of x tilde and sigma 2. You have another input. Then continue this procedure until the end. Does it make sense? What is happening? You start with the noisiest version, generate sample. Use that sample to initialize another LMC with a score function of a lower noisy version. Then output another sample. Continue this procedure until you use the best the best score function, which is sigma L. Yes.
This part I'm not understanding. So once you have,
let me once you are asking your question, I rewrite this procedure. Okay, ask your question.
so every time you use a new sigma I,
Yes.
it's like when you are training, you apply that like on a fresh data set. But now during inferencing, you're applying subsequent sigma i's on noisy versions of the data set.
What is the property of each sigma S theta? Assume that I give you should pay attention to what is S theta, okay? S theta of X and sigma. What happened if I input X to this score function and then just one step of LMC? What happened in the output? What is the output? How the output is changed in expectation, not in the one data point, in the expectation. If this X is coming, if the probability, Q sigma of X is for this one, and we have Q sigma of X tilde here, which of these sign is probable? Is the most probable?
The non-noisy one.
This one or this one? The above or the... You use the score function, you use the score function of this distribution. When you use the score function, it means that you are increasing your probability in terms of that distribution. So the probability of the new sample will be higher as a result of, for example, one of the MCMC methods, because you use the gradient of the direction coming from this direction. Okay, I mean this is LMC, one iteration of LMC, one iter. Now I start with X tilde, input this one to S theta of, let me check. Yes. I want to make sure that the subscripts are correct, all of them. This is the noisiest score function, and I have this output, X tilde 1. I know that this sample does not have the problem of slow mixing because the data set is very noisy. Then I input the output of the previous section into a new LMC with this score function. What happened? In terms of Q sigma 2, I am increasing the probability of this data sample. Q sigma 1. Which of these two distributions is nearer in terms of conceptually, is nearer to your true data? The second. And also, you are making more probable in terms of this distribution your data, okay? So you are making better samples from your true data model, from the true data distribution.
I see. So the input is also like a valid input?
Yes, you can input anything. Previously, for the Langevin Monte Carlo, we start with a sample from a Gaussian noise. But you can even use your training data samples, and a good model should not change it because that's a really great sample. It is really coming from the true data distribution. It just have some minor changes around itself. It does not put it, for example, in another point of the space. A good sample. And you can input with any sample. It is just responsible to increase the probability of that sample, the new sample at the output. Yes.
You mentioned earlier that the noise for the input that is plugged into S theta of X and sigma 2.
Yeah.
The noise should be also matching with the theta 2. Sigma 2.
Sigma 2, yes.
But here in the bottom figure, the noise added to the input is sigma 1.
Sigma 1, yes.
Or the noise, actually, I don't know.
There is no noise addition here.
Yeah.
You just use the score function resulting from sigma 1 to denoise this X tilde.
Okay.
You do not add any noise here, okay? What is this score function? This score function is the score function of this distribution. It means that when you use it LMC with this score function, you are increasing the probability of your data with respect to this distribution. You are reaching a more probable data point in terms of Q sigma 1, which is a noisy, very noisy. As a result, we do not have the problem of slow mixing. At the same time, it is not a great sample because it is very noisy. To update the sample, we use the output. This is exactly the same. We use it and then increase the probability of this input in terms of the new distribution, which is nearer to your true data samples. And you output x tilde 2.
Yes. So here, like the noise of the input and the noise of the S theta are not matching.
The noise of the input is this input.
Yes.
This input is a completely noise. Is a noise because you are sampling. You have nothing.
Yes.
You want to generate sample from, for example, MNIST dataset. You have this noise condition score function. You have this one. You input it with a sample coming from standard Gaussian, and then hopefully the output would be a sample of MNIST. Okay? This is complete noise. Completely noise. This score function change it so that the probability of, we know that the complete noise has a low probability in Q sigma 1 because Q sigma 1 has some intuition from the true data samples. When you pass it through the LMC, you have something which is more near to MNIST samples. But it is again it has high level of noise. X tilde 1, yes. It has high level of noise. You start pruning the sample so that you at the end you have a great sample of MNIST. Make sense? We continue this procedure. At the end, we use LMC using S theta of X tilde and sigma L. We know that we cannot start, this is L minus 1. Yeah, we cannot start with this score function because we have slow mixing of Langevin dynamics. In terms of what happened in reality, something like mode collapse or something, you will see something very similar, but in context, something which is more probable is not observed at the output of this model when you just use S theta of the last section. But as a result of using this procedure, you have samples with while the mixing problem is also solved. Any question? And this is the final algorithm of Annealed Langevin dynamics algorithm. This is the algorithm that we sample from the data. You have a trained model. You have this one. You input it to a Monte Carlo method. This is a revised Monte Carlo method because it should accept a score function that has the information that it can have the information of the noise level. So the input is sigma sequence, the score functions T and epsilon. You start with the sample X tilde 0. Then for L iteration, this is the outer iteration. This is iteration number 1, this is iteration number 2. This is the I. I equal to 1, I equal to. At the end, you have I equal to L. What happened for each of them? You select a step size. You see that the step size is also a function of the noise level. And then for T iterations, you exactly run the Langevin Monte Carlo, previous version. Why? Because you want to sample from that ith level. At the output, you have X tilde T, and then you replace, because at the end, you have T, uppercase T, and you output that uppercase T as the input for the next one. Exactly what I have written here. This is exactly the same as what we have here. Nothing changed. And this is exactly Langevin LMC. LMC without accept or reject. pay attention to the fact that it does not have the accept or reject procedure. Yes?
XI, like the line 9, X0.
Yeah, because x0 is again used as the start, okay? I think that this one is,
Mistake.
yeah. This one should be x0. The x0 is the initialization of the sample you input to Langevin. Yeah. You use the last one of the previous part as the start of the next one.
Okay, so but here in this pipeline there is no X0.
x0,
Because in the for loop,
assume that you are t equal 1, x1, x0, x tilde 0. You use x tilde 0 to generate x1.
what about X2?
x2 uses x1. It is an LMC.
I know. But like when X1 is, X2 is acting like the XT minus 1.
You know, I start for t times, I just focus on one level of sigma, and using this procedure, I start from x tilde 0, and at the end I have x tilde t. And then output that x tilde t as the input for the next. Yeah. Any question? Yes. ZT is the normal sample. If I do not write it here, it's my. Oh, sorry. This is VT. This is exactly what we have. We have some randomness in LMC. They are the same. I will correct it. Okay. Thank you. So this is the last part of age-based models, and this is the result. If you sample from a fixed value of sigma, which is almost near to your true data, it means that a less noisy data set, you have something like this, and you clearly observe that the resulting output is not aligned with your true data. But if you use ALB, you see that the resulting algorithms also understand the component ratio. And as a result, you have the same number of samples in both groups.
Sample B, when we're using LMC there, are we not doing the rejection of the metropolitan Hastings correction?
Yeah, we are rejecting that step, yeah.
Are we able to do that step? And if we do, how does that change?
I think there is some guarantees for that version 2, but in practice, when you're rejecting that, you also get the samples, the generated samples are great quality. Yeah, but I do not exactly know what is the difference in the convergence rate or the convergence itself. Maybe there is no exact guarantee to come for convergence.
Why does the ALD solve the problem of not knowing anything about the mixture ratio?
You know, when using ALD, what happens? You are not working with these data set anymore. What are you working with? You are working with a large-end data sets. Does it make sense? Something like this, not out of the box. Something like this. And each of them are enlarged based on their population, each of the components. First, you start by generating samples from this distribution. And in these distributions, because they are enlarged, as a result, there are some information from what was the problem previously? When we talk about land, this was the problem. Now assume that something like this happened. Then we have the log of the summation of the two terms. And because one of them was equal 0, we see that we have the problem of mixing. But in this case, whenever each of them is non-zero, the other one is also non-zero. So you cannot assume that this part is 0. And you have the effect of the mixing. Does it make sense? Let me check the previous figure we have. This one. Why this problem happened? This problem happened because of this almost zero part. If this part is not almost zero, everything will be, you have information of pi 1 and pi 2. Does it make sense? Because of this zero, you have the gradient of the log of the multiplication, then you have the logarithm of the first one, and the logarithm of the first one is 0. But if you cannot assume this part is 0, you do not reach that point that you omit pi 1. So adding noise can solve that problem. And if the noise is enough, then you are certain that the problem is solved. Okay? Any question? Yes.
When we were covering MCMC models, they're capable of approximating bimodal distributions, correct?
Yes.
And that came from their ability to have the accept or reject part of the algorithm?
Yes.
So would that accept or reject part of the algorithm help us in this case, or what prevents it from you just running else or mala instead of LCMC?
Generally, when you are trapped in one of them, then escaping from that is not generally suitable. Especially if you increase the variance of that proposal distributions, then you miss the information you gathered during your training, because every point becomes almost equally probable. Then you increase the variance. Okay. There are some trade-offs there also. If you increase that problem to explore any place in the space, then you lose your information you gathered during, for example, 1,000 iterations. And in practice, you are working in much more higher dimensional space, 1 million dimensional space. And the problem becomes more and more sophisticated there. Okay? Any question? So I think we ran out of time. Just look at these images. What is this? We go back. Look at these images generated using noise condition version. Starting from complete noise, you change it using the noisiest version score function, then less noise, less noise, less noise, less noise, less noise until the end, which is the nearest one to your true data distribution. And as a result, you see that the nearest one to your true data distribution is really high quality image samples, face samples. Also, this is a sample from C-Farten dataset. These are samples from MNIST. These are samples from, again, C-Farten. These are samples from Solvay dataset.